Welcome to the fourth video in the Input Analysis and Modeling module, and in this video we'll look at goodness of fit. So in previous videos we looked at hypothesizing distributions and estimating parameters, and so at this point we assume that we have some data and we have hypothesized a distribution including parameters, and now what we'd like to do is essentially assess the quality of that fit. And so here we see a histogram of some sample data. We have a sample mean and sample standard deviation given here, and we look at that distribution, we might assume that the data appears fairly normal. And so the question in goodness of fit is, well, how good is that hypothesis that the data is approximately normally distributed? And of course, we have that same question regardless of what the distribution that we're hypothesizing is. And so what we'd like in this video is to look at a quantitative method for doing that. And the method we're going to look at is a goodness of fit test called the chi-square goodness of fit test. In general, goodness of fit tests are statistical hypothesis tests. So we're testing the hypothesis that the observations constitute an independent sample from a particular distribution. So this is our hypothesized distribution. In the previous case, it would be a normal distribution. So our null hypothesis is that the xi's are independent, identically distributed random variables with the distribution function f. A couple of notes on goodness of fit test. First, that failure to reject the null hypothesis shouldn't be interpreted as accepting H0 to be true. Remember, when we do hypothesis testing, we're trying to collect evidence to reject the null hypothesis, and just because we don't have enough evidence doesn't mean the null hypothesis is in fact true. And secondly, goodness of fit tests are not very powerful when we have small to moderate sample sizes, and when they have a large number, then the tests often reject H0 since really small differences between the hypothesized distribution and the data tend to be detected. So with those two things in mind, the goodness of fit test can still give us some preliminary information about the quality of our of the fit. So the chi-square goodness of fit test is essentially a formalization of what I would call the histogram test. And so you can see in the figure we have our sample data represented by the histogram, and then we have the hypothesized distribution represented by the red curve. And so essentially when you look at this and try to assess the fit, visually, what we're really looking at is deviation between the histogram cells and the curve. And so when we do a goodness of fit test, what we're really doing, or chi-square goodness of fit test, is comparing the number observed in a particular cell. So that's the number that we observe with the expected number, which we can get from by integrating the distribution function. So there we go, that's what we expect. So we're comparing the number observed with the number expected. And we're systematically doing this over all of the bins in our histogram. And so formally, it looks like this. We divide the range of the fitted distribution into k adjacent intervals. So those k adjacent intervals are what we see here. So you have 1, 2, 3, so on. Then we're going to tally nj, cap nj, which is the number of the observed values in each interval. So for each interval, we'll know how many observed values we have, which is this value here. Then we'll compute the expected value, or expected number of observations in each cell, by computing this probability. And this is what I mentioned before of integrating the function f, or if we have a discrete probability function, we just sum the mass function components. And so the test statistic becomes this difference in each cell. So this is the difference between expected and observed in each bin squared, so that we can consider both negative and positive deviation, and we just sum that up and then divide by the expected number. And so if the fit is good, then we would expect the test statistic to be small. As the deviation between expectation and observation gets larger, then we reject the null hypothesis that the fit is good. To determine this notion of sufficiently large, we look at this test statistic chi-squared. And so if H naught is true, in other words, if the sample is from the hypothesized distribution, then the test statistic converges as n goes to infinity to a chi-squared distribution with k minus m minus 1 degrees of freedom. So k, remember, is the number of bins. M then is the number of distribution parameters that we estimated from the sample. I'm going to come back and talk about that in a little bit. And so here's a picture of a chi-squared density function with k minus 1 degrees of freedom. And so what we're doing is we are determining what the alpha level is, in other words, the probability of falsely rejecting H naught, a value that's typically 0.05. And then we're setting the rejection point to be the critical value, chi-squared, k minus 1, 1 minus alpha. And so anything, when we compute the test statistic, anything that's larger than that critical value, we reject the null hypothesis. Anything that's smaller than the critical value, we don't reject the null hypothesis. Note also that this 5% probability, or the alpha percent probability of falsely rejecting H naught, is because we can have a sample, in our case from a normal distribution, for example, where the computed value is in fact greater than the critical value, and that's what this alpha probability represents. Okay, so let's look at an example. In the example we're going to look at is we're going to sample some uniform random variates from the RAND function in Excel. So here we have 25 observations, so I just used the RAND function to generate these. And what we'd like to do is test these values to see, hypothesize that they're sample from a uniform distribution, which is what we expect to happen. So we can create a histogram. So what we did was we created a 5-bin histogram, and we then sorted the values and counted the number of observations that we saw in each cell. So by dividing our space, dividing the range between 0 and 1 into 5 cells, we then have the observed values in each cell. And we can compute the chi-squared test statistic by comparing those against the expected number. Since we have a uniform distribution and we have 25 observations and we divided our range into 5 equal sized bins, we expect there to be 20% of observations in each cell. So in our case, the probability Pj is equal to 0.2 for each cell, and when we multiply that by the number of observations, the expected number in each cell is 5. So for example, in cell 1 we have 3 observed values right here. We expect there to be 5, and so we compute the component of the chi-squared test statistic by just taking the difference between those and squaring it and then dividing by that probability. And the test statistic value is then 3.76. If we compare that against the critical value, which for Excel I just used the chi-inverse function to get that for us, with an alpha value of 0.05, is 9.4877. And so our decision in this case would be do not reject, because the test statistic value is less than the critical value. And so back to our slides, we have the region here that we computed is 9.7, and we're somewhere way back here at 3.6, so we don't reject the null hypothesis. We have that also in the slide where I guess I already drew it out here. So we have the chi-squared density function with 4 degrees of freedom because we had 5 bins, so it's k minus 1. Note that we didn't estimate any of the parameters with our data. We just assumed that we had a uniform distribution between 0 and 1. And so again, we do not reject the null hypothesis for this case. And so next, the question we have, and for the general chi-squared goodness of fit test, is how did we determine the bins? For our example, we simply took the range space and divided it into 5, and then we made those bins equal width. And so the question was, why did we do that? Well, we're going to use a very simple rule of thumb for determining the bins. We're going to have 3 rules. One is that we want to have more than 3. 2 is that we want npj, in other words, the expected number of observations in each bin, to be greater than or equal to 5 for all j. So for all bins, we want to have the expected number to be greater than or equal to 5. And finally, we want equiprobable bins, equiprobable. And so equal probable bins essentially means that the pj value is equal to p for all j. So we're going to pick a value and then we're going to make all of the bins have equal probability. So for our uniform distribution, that was very simple because we simply divide into equal width cells and we end up with equal probable cells. For other distributions, this won't always be the case, as we'll see in our next example. So for our next example, let's suppose that we have 100 observations and we want to hypothesize a normal distribution. So we want to hypothesize a normal distribution. And so we have our normal distribution here, looks something like this. And let's say that we want to set the k value equal to 6. And so if we look back at our rules, we certainly followed that first rule. K is greater than or equal to 3. If we make the cells equal probable, meaning we're going to have the same probability for each cell, our probability P is going to be 1/6. And so this is approximately 0.1667. And our second condition says npj is greater than or equal to 5 for all j, and so n is 100, so npj will be 16.67 for all j. And so having 6 equal probable cells will certainly meet all of those conditions. So the question is, how do we get that? Well, what we need to do is we need to divide the space, the range space, which goes from -infinity to infinity, by the way, into equal probable cells, so that the probability is 1/6 here, 1/6 here, 1/6 here, and so on. And so in order to do this, we need the 1/6 quantile, the 2/6 quantile, the median, the 4/6 quantile, and the 5/6 quantile for our normal distribution. And so we have an example of that in our Excel version. So here are my 100 observations, and we looked at two cases. The first case is, let's assume that we know the parameters of our normal distribution. In this case, we have a normal distribution we're assuming with a mean of 50 and a standard deviation of 10. We can compute the cell boundaries by just simply using the norm S inverse function. So here's my cumulative, and then use norm S inverse, and then convert that to our normal distribution with the mean of 50, standard deviation of 10, and then we can get our cell boundaries. That way. And so then once we have our cell boundaries, we can compute or count the number that fall into each cell, and then we can compute our test statistic according to the chi-square formula. And so in this case, our total value, or our chi-square value, ends up being 7.04. The test statistic, so now we're using n-1 or k-1 degrees of freedom, so 5 degrees of freedom and a confidence level of alpha of 0.05 is 11.7. On the other hand, if we use our data to estimate the parameters, this is where the m value comes in our k minus m minus 1, we have the same data, but now the mean and standard deviation are estimated using the data. So instead of just assuming it's 50 and 10, I actually compute the sample mean and compute the sample standard deviation. And so the sample mean and sample standard deviation, because I computed those, will change the boundary values slightly. And so we end up with a different test statistic value, in this case of 4.64, but we also have to account for the fact that we've estimated those parameters, and so our critical value is also 7.81. So our critical value has gotten smaller, essentially making it easier to reject the null hypothesis. But in this case, we still don't, because 4.64 is still less than the critical value of 7.18. So in summary, the chi-square goodness of fit test, the basic idea is that we are comparing, we're dividing the range into adjacent cells, and we're comparing what we see, the observed values, with what we would expect to see in the hypothesized distribution. And we're using a standard formula to do that, or a standard computation, so that the test statistic follows the chi-square distribution, which lets us do the hypothesis test.